Okay, and Ross is here. Ross, are you with us?
Yeah, you hear me?
Yeah, perfect. Yeah, so everybody, let me do this real quick. So Ross, you joined us a couple of weeks ago. Actually, I think it was March 12th. And so you were talking at the time about the device you were building. Today, you're going to be presenting on same device. It's the rhythmic balanced interchange, the RBI machine, which produces, or you're hoping will produce, reactional thrust using an inertial propulsion design. So this is based on, this is kind of a mechanical device. And I believe last time you were with us, you had one armature that was working, and you did kind of a test, and it was moving around with that. I understand that you've got the other armature. You've got this thing a lot closer to completion. So let me turn things over to you, and you could just kind of walk us through. And if you want to start from scratch and just go through the whole thing from the top, that's totally cool, because we have folks, again, like on YouTube and stuff like that, who may not know. They maybe didn't see your last presentation. So it's all yours, sir.
All right. Well, it's actually is all done now. It's 100% finished, so it's right behind me. It's over 300 pounds. It's got two 40-pound gyroscopes, so it's about 80 pounds of rotational energy there. And it's got two electric motors. This one is about at least 10 horsepower. That's probably close to 10 horsepower. So they're both connected together. So we're talking about 20 horsepower right there of power that are spinning these small little gears down here, which are channeled up through these number 40 motorcycle chains, which spin these two gyroscopes. So I wanted to do a couple physical demonstrations first. So you see on the machine, I actually color coded. This is, I'm going to call it point mass 1, the red one, or I could do it 2, whatever, but it's red and blue. So there's 2 point masses, and if I spin the machine around, you'll see I also have 2 point masses, red and blue here, corresponding to the same point mass. So this is one physical gyroscope right here. So I actually did the same thing. I just painted a little blue and a red dot. So I'm focusing on 2 different point masses on a gyroscope that are separated by 180 degrees. So 180 degrees separated, and through their middle is this point called the center of gravity, which is sort of just an anomalous place. But another point I want to say, I was going to connect these 2 together with an aluminum rod, but all you need are 2 point masses. So just 2 point masses spinning around in a circle, that technically is a gyroscope. And then I want to show this. So this is one gyroscope, and then this is an identical gyroscope. So if I connect these 2 together with the same shaft, even though they're 2 gyroscopes, they're connected via a shaft down the middle. So they become one gyroscope. So I'm trying to demonstrate that even though this machine has 2 different gyroscopes, they're connected down the center by the same shaft, and it's a keyed shaft. So this is acting, both of these gyroscopes are acting as one gyroscope. It actually was one gyroscope, but I cut it down the middle and separated them so that I could get these chains to the middle to spin them. And I'd like to first say that this whole theory is from Mike Marsden, his Mac-Quan 1. I mentioned this last time, but I want to say it again. I also want to mention a few names. Cleveland Savage helped me a lot with this. He started the Anti-Gravity Club, which I joined in 2008. I had actually been following inertial propulsion since 1998, and I found him about 10 years later in 2008. And then later on, Zach Mueller came along, helped me out, and currently it's Brian St. Clair. He's working on the Pi X, which is a basically the same thing as the Mach 1.1, but we're calling this a test, sort of a test machine to demonstrate how the Pi X or the Mach 1.1 works. So Tom, can I share my screen?
Oh, yeah, sorry. Yeah, go for it. Just hit the share screen button.
Okay, I made a animation so that I can kind of demonstrate what's going on before I actually show the machine. I made a stop motion animation, so because it's kind of hard to understand a lot of these concepts.
Yeah, no, absolutely. Yeah, just go share screen. So it's the green button down the center bottom of your screen. And then it's going to make you pick the window.
Oh, I gotta change my settings real quick to allow it. Okay.
Oh, you're probably on a Mac.
Yeah.
Yeah, mine does the same thing.
All right, I'm gonna have to leave and then come back, okay?
Sure. Yeah.
Right back. I'm gonna have to leave because the Mac won't let me do it unless I leave and then reopen it.
Okay. Yeah. Well, we'll hold on for just a sec then. That's fine.
Okay, I'll be right back.
Okay. Slight technical delay. That's nothing new to us, though. Oh, yeah. Riccardo, everything okay? Oh, here. Let me.
Just want to ask a question. Just looking at that rig, I'm wondering to myself how he hasn't managed to punch holes in all of his walls.
Yeah. Well,
very impressive.
Things like that, I'm really excited about that. The thing that I like about our conference is that we have a mixture, right, of hands-on and theory,
Yeah.
and I think it's really good to have that mixture.
Yeah, look. My view is, no matter what someone puts forward, but any kind of experimental setup, if they've gone to the trouble and the investment, both emotional, financial, and intellectual investment of doing it, I mean, that's fantastic. I mean, good luck to them. That's just so good. It's worth seeing, you know, definitely.
Yeah, well, and Ross, your device, to me, your device reminds me a little bit of James Cox, Bootstrap Cox. He had a device. I think his was like a lawnmower engine back in the day.
You mentioned him. I actually looked him up. I found his patent. He never actually built it though. I don't.
He did. He built a few variations, but from what I remember, and I'm not sure if he passed or if he's still around. I think he probably passed because he was older, but his stuff was like shake and bake, you know. I mean, it was all over the place. But he was using the machining and the engines of his day. So
listen, Ross, just before you get started, I'd just like to ask you a question. Have you put any holes in your walls with that?
I actually did. I put a hole down right here in this wall. It smashed through the wall, and I had to fix this whole wall right here.
Okay, all right.
It went through the wall.
Yeah. Well, so yeah, Ross, let's fire up the animation, see if you could share that screen, and then we'll keep going from there, sir. There we go. Perfect.
All right, so you see these, this picture?
Yeah.
All right, so I also color coded them blue and red. Do you see my mouse too?
Yeah.
Okay, so that's like, I guess that would be like point mass 1, that would be like point mass 2, and that would be the center of gravity. The center of gravity is more of like an anomalitic, weird, you know, it's not really like it's more of like a universal thing. It's like a singularity, I call it. It's, I don't know. A lot of people who work in inertial propulsion want to worry about the center of gravity or manipulating that. I don't think you can manipulate the center of gravity. I don't think you can interact with it. I think you have to interact with the physical manifestations here in our universe, which are the, you know, physical point mass 1 and point mass 2. So what you're trying to do is make, you know, manipulate this and this to make the center of gravity go straight. So you're trying, that's the whole point. You're trying to take a lot of mass that's spinning around and around in a circle and somehow trick it to make the center of gravity move along a straight line. So that's more of our focus, is we're actually focusing literally on actual physical phenomenons, the point mass 1 and the point mass 2. So last time I mentioned this as well. So as point mass 1 goes up and to the right, point mass 2 is going down and to the left. So they're always doing the exact equal and opposite reaction of each other. Because I want to also point this out. Nothing wants to move in a circle. Everything wants to move in a straight line. Everything. There's no reason why a gyroscope wants to move in a circle unless there's something balanced. These two, there has to be at least 2 points, and they have to be equally weighted and, you know, balanced with the center of gravity. That's why they spin around in a circle, is because they're in a balance. So as one point mass is moving up and to the right, the other one's moving down and to the left. So they're always doing the exact equal and opposite reaction of each other. So as one goes up and to the right, the other one goes down and to the left. It's exactly the opposite of the other. So another point I want to say, if these 2 points got separated at any point, if you took a pair of scissors and you cut this down the middle while these were moving, this one would go straight and this one would go straight. So they would no longer be going in a circle because they would no longer be connected. So like if you cut this connection in between the middle, this blue point would go up and this red point would go down. So that's another point I want to make. So this is a very simple stop motion animation of the 2 point masses spinning around in a circle, doing the equal and opposite reaction. And notice these 2 dark lines over here. That's the physical manifestation in the machine that I just built. These 2 arms are actually going to move back and forth and keep up with the point masses, you see? And that's what we call a constant linear component. You have to have something that we call a constant linear component, something that can reach out and touch those 2 point masses and actually physically interact with them physically, right at, not from the motor itself, not from the center motor, not from the drive shaft. You have to do it way out on the periphery where those straight lines are. So we call those constantly linear components, or constant linear components. And so I want to show this point at this point, I put in an orange arrow. So the machine is, you know, spinning around in a circle, like this, spinning around a circle. When it reaches this point, the left side is now being decelerated by that linear component. So once you start decelerating it, which stands for the orange arrow is trying to decelerate it down in a straight line, because it's moving, it's about to move up, it's moving up. That blue point on the left right now, it's moving up, and then it's being decelerated while it's moving up. So if you only decelerate that one point, what happens is it carves out a long trajectory. It carves out a long trajectory, while the other point mass on the other side, which is not being directly decelerated, it's connected by the yellow line, the rigid yellow line, which is the gyroscope. So it does an equal and opposite reaction. It carves out a smaller radius. The one on the left side that's being actively decelerated with the orange line is carving out a longer radius. And the point mass, the red point mass on the right, which is not being actively decelerated right now, is carving out a shorter radius. And now that point mass that was the blue point mass on the left that was moving up, now it's about to move down. So now, instead of being a decelerative force, it becomes an attempted acceleration force, because now it's not moving up, it's trying to move down in the same direction of the force. So it becomes an attempted we call it an attempted acceleration force. So there's the orange arrow on the right side. As you accelerate downward, that point mass now carves out a shorter radius, while the other point mass on the left side now carves out an equal and opposite reaction, which is a longer radius. And then notice the orange arrow that's on the right, it switches to the left side. Our spring now switches to the other side. We have a second spring that activates to the opposite side of the machine at this point, physically changes to the other side and starts to decelerate that point mass, the red point mass. So it does the same thing. It decelerates it for 90 degrees, decelerates it, and then it accelerates it for 90 degrees down. And see, the other point is always doing an equal and opposite reaction. And then it switches again. See, it gets here, and then it switches. The spring switches. The spring is on the right side, now it switches to the left side. Then it decelerates for 90 degrees, accelerates in a downward attempted straight line force for 90 degrees. Then it switches. It decelerates for 90 degrees, accelerates for 90 degrees. And I find this pretty cool that on the left side is where all the deceleration was happening, and on the right side, all the acceleration was happening. And the radiuses on the right, the geometrical radiuses are smaller than these. And I actually graphed these circles. I actually graphed them, and it's pretty crazy. It actually corresponds. The size of this circle is related to the size of this circle, which is related to the size of one of these bigger circles. So they're all interrelated, like almost like a spiral. So I found that very interesting, mathematically speaking, that this circle, one of these circles, is related to this circle, which is related to one of these circles. Maybe I'll show you a video. I actually made a video of this instead of just stop motion to kind of show it. But also, I want to point out, look at the center of gravity. I actually made a lime green, you know, color tracking to track it while it's going along there. So it's, let's start over from the beginning. So normally here's a gyroscope spinning around in a circle. And in our machine, we have these linear tethers. And this is what happens. So that's the theory. Let me play this little video real quick. It's the same thing. It's just I want to show it there with a video. There's the deceleration and then the acceleration. Then the deceleration, then the acceleration, and the deceleration, then the acceleration, then the deceleration, then the acceleration. So I think that's all that I wanted to show for my screen. So I'm going to stop sharing. All right, you want me to show the machine now?
Yes, please, 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 please. And so Ross, I've got you. Yeah, you're on Spotlight, and let me see. So folks can't. Let me see. People cannot unmute themselves for right now. So yeah, the floor is all yours, man.
So this is a braided stainless steel 1/8 inch wire, which is fed up from this spring. It's like this really heavy duty spring. So right here, there's slack. It's not doing anything on this side of the machine. It's not until it gets here that the slack now reaches, it's now reached this point, the blue point, point mass 1. So for this 90 degrees, it's going to be decelerated, but in a perfectly straight line. So it gets decelerated by this braided stainless steel wire from the spring. It just got decelerated and decelerated. But then when it reaches here, it's now about to go down. So now that spring is going to accelerate it down. So it accelerates itself down from the spring. Then spin the machine around. So now here we are with this side of the machine. It's now going to engage the red point mass and decelerate it for 90 degrees. And then accelerate it down for 90 degrees. And then we switch back again to the blue point. Decelerate for 90 degrees. Accelerate for 90 degrees. We're back here to the red point again. Decelerate for 9 degrees, accelerate for 9 degrees. So that's basically how difficult it is to create a machine to do this. It's not easy. It's very hard. Let me show you, I can actually do it by hand. I'll show you from this angle. And there's actually a balance point. I found that there's a buoyancy point. There's like a buoyancy point right here through the middle. It's balanced like right here. See how it kind of bobbles back and forth, and then it. So I found that was pretty interesting. You want me to turn it on?
Okay. Sorry about that, Ross.
That's all good.
Y'all done?
You want me? I'm gonna go ahead and turn it on.
Do it. Turn it on. Turn it on. We want to see this thing run.
I'm gonna use the powerful motor this time. That's the weak motor. That's the more powerful motor. But it's got some kick with the powerful motor. I mean, it's like 10 horsepower or something.
Safety glasses.
Yeah, and I gotta use the stronger electrical circuit because I broke the other electrical circuit the other day because I chose the weaker circuit, but I have to have them really powerful electrical circuit to run this because it takes so much energy to move this thing.
Yeah, put some safety goggles on. If anything flies off, you don't want to be maybe stand off to the side of it, not in front of it, right?
So should I do it kind of like at this angle, maybe?
Yeah, I think that'll work great. This is yet another first for APEC.
Yeah, it's pretty cool that it's finished now, so the arms are like actually going back and forth like that, right? You know, so there's 2 arms now. You know, it's pretty cool. I mean, I can't believe this whole thing came together and it like in my mind and it actually works. It's pretty crazy. And the crazy part is that it doesn't want to start initially. I have to kind of like kick it a couple times to get it to finally go because it's so much spring. It's like 70. Each one of those are like almost 80-pound springs, you know, extension stretchy springs that are 80 pounds of twing. So it's like really hard to stretch those springs, you know what I mean, on both sides. There's 2 of them. So that's like 80 pounds of upward decelerative and acceleration forces being imparted all the way on the periphery of the gyroscopes, not in the center. We're talking about you're reaching out and touching the very periphery of the gyroscopes where you can, you know, extract the most amount of energy way out there. Let me get it started. I was just making sure my cat's not around. All right, I'm ready. All right, was that good enough? Because it's 7:30 and I don't think I could do that again.
Yeah. I mean, it's completely up to you, but
Yeah, let me turn it one. I'll do it one more time sideways like this. All right, good enough?
yeah, I think it's awesome. I think that is an awesome device.
It's got power. I mean, once it gets going, but it's still decelerating and accelerating at exactly 90-degree angles like a wave.
So if I can ask, what are your plans in terms of testing this thing?
So yeah, because I was initially going to put it sideways on a bunch of wheels and put a platform of wheels and take it out to the middle of a parking lot and see if it can go across a parking lot. Brian's saying I could either do a pendulum, like a teeter-totter. I'd have to get like a big, huge teeter-totter in here and kind of weight it down and then have it so it's just barely enough to lift off the ground and then turn it on and see if it, like, you know what I mean?
Yeah, the problem with the pendulum is you'll have so much instability that it may, I don't know if you could keep it stable to measure the weight, right?
I'd have to have a really powerful like pendulum, like I'd have to get like a $10,000 children's steel teeter-totter and do it that way and like weld it to the thing.
Yeah.
Like really power and then bolt it down into the pavement or something. And something like that. Or he's also saying I could buy really big veterinarian scales for like horses, you know what I mean, like 500-600 pound veterinarian scales, and put them out here, you know, on the ground, and then turn it on and see if it's creating some upwards thrust. But I can't imagine that it's not producing some kind of upwards thrust. I mean, to me, because it's like almost wanting to jump off the ground. It seems like it's just so much like spring energy, just lifting it up. I mean, it's just so heavy. It can't float, obviously. But it's, you know what I mean? If it could produce like 10 pounds of thrust, I mean, that's enough right there, you know?
Yeah. Well, Ross, let me do this. So if that's it for the presentation, do you want to get a Q&A? Let's go to Q&A then. So, but let me do this. So I removed the spotlight. Let me put this thing on gallery view. People can unmute themselves. Before anything else, everybody, please give Ross Small a giant hand. And I see Brian St. Clair is with us as well. So